In this exercise, we're going to look at some of the stress analysis capability by taking a beam from the content center and testing it. So let's go to the home button up here, say open, and open from content center. And from the open from content center dialog box, I'm going to go into structural shapes, expand it, and I'll pick an I-beam. I'll double click on the I-beams, and there are a couple of families of I-beams there. I'll double click on the first of the two. And up comes this dialog box giving me a number of different variations on that I-beam. I'll go for the 400 by 66 I-beam and stipulate its length at 10 meters. When I say OK to that, given a chance to name the beam and to save it in a location, say yes to that, and then it comes. The first job here is to reorient this I-beam, so I'm going to use the view cube, I'll bring it in, and right click on the home button, and say set current view as home fixed, fit to view, and we're set up and ready to go. I'm going to go into the environments tab and pick stress analysis, and that will set up the capability for us, and I'll say create simulation. And from the create new simulation dialog box, I'm going to accept all the defaults and I'll produce a static analysis. Say OK to that. And the logical, sensible first thing to do to this beam would be to constrain it in some manner. In the constraints tab here we have three different options: fixed constraints, frictionless constraints, and pinned constraints. I'm going to set up two fixed constraints, one either end of the beam, and then I'll apply a load. So I'll say fixed, and the location button is currently depressed, so if I zoom into this end here, I'm going to grab that edge right there and say OK. Zoom out, and I want to grab the corresponding edge at that end, so use the view cube to turn it around. Say fixed, that edge, say OK, back to home view. If I go into the constraints folder here and expand it, I can see I've got two fixed constraints. That's reassuring. I'm ready to apply a load now. I'll click on the force button to apply the load. The location button is depressed currently, so the first thing to do would be to decide where the load is going to be applied. I'm just simply going to apply the load to this top surface here, so I'll zoom in to make sure that I get the top surface there and not an edge. And when I zoom out, I'll see that by default Inventor applies the force bang on centre. I want to set the magnitude of the force just now, and I'll go for 10 kilonewtons. I'll say OK. So just to summarise, I have the beam constrained at both ends with fixed constraints. I have a 10 kilonewton force applied on the top surface centrally, and the next thing to consider would be gravity. I'll click on the gravity button, and the appropriate value has already been applied, and I just need to say which direction. So again, I'm going to zoom in and grab that top face and say OK, and we're ready to now simulate. I'll say run, and that starts the process of simulating these conditions. And we can see the results of the analysis here. The deflection in the beam has been exaggerated to quite an extent just to show what's going on. Of course the beam wouldn't deflect to that value. We can see the levels of stress indicated over here, and the corresponding stresses colour coded in the beam here. If we zoom right away into this corner here, we can begin to see that there's stresses building up down here, which would make logical sense given that this is one of the points where the beam is constrained. If we were interested in displacement rather than stress, we could double click on the displacement report here, and Again, we've got an exaggerated deflection, but the colour coding represents the amount of deflection described on the scale to the left here. And in the red segment here, we've got a maximum deflection of 2.439 millimeters. So for those conditions supported at this end and this end against that load and gravity, we would have a maximum deflection of 2.5 millimeters. Useful to know. One neat feature that Inventor has is an animate option, and we can take this displacement report and watch it in action. So having analysed our beam in this manner, we can click report and get a comprehensive readout of a huge number of different properties in enormous detail, textual and graphical. But of course all of this really comes into its own when we're not using simple beams, but we take realistic objects and apply actual forces to them in order to put some design intelligence into our model. Let's go through that process now. For the purposes of a realistic stress analysis, I've opened up this suspension arm from the racing car. As before then, let's go into the Environments tab and say Stress Analysis and Create Simulation. We'll say OK to the Create New Simulation dialog box. And job number 1, as before, is to consider constraints. At this stage we have to use our knowledge of how this part fits into the rest of the model and ask ourselves how this is being constrained. We're going to simplify the answer to that question by saying the suspension arm is being constrained at this point through this hole, that point, this point, and this point. There are complicating factors in that there are parts bolted on here and round the other side, but for the purposes of the analysis, we'll just deal with the 1, 2, 3, 4 points as described. So we'll say 4 fixed constraints, location, here, we'll grab all 4 simultaneously and say OK. And then for force, let's say the suspension arm is loaded on this top surface here to a value of 5 kilonewtons. We'll OK that. And the software will pick the dead centre of that top surface. And we'll include gravity as well, of course, on that same top surface. OK that. So let's simulate these conditions now and see what we get. Click on Simulate and Run. That'll just take a few moments to compute. And we get quite a large deflection indicated here. Let's look at the stress levels. So for the stresses built up, we have, as expected, lots of stress around about here and here, and here and here. Interestingly, some round about here, as perhaps the part is beginning to fold at this point. Let's look at displacement, and that's quite a large displacement there, 7 millimeters displacement. We'll just animate that to see it. That's quite useful. I'll OK that and point out to you also that sometimes the deflection is less noticeable, in which case we can use a scale factor here to exaggerate slight movements, a 2 to 1 and a 5 to 1 scale factor. And I'll animate that again. Okay, so I'm sure you don't have to try too hard to begin to see the direct relevant uses of this kind of information when it comes to improving on your design.